All right, the projector's still warming up, I guess. So I wanted to circle back to the midterm. And so I thought I'd do something, because I did this in my other class. And so I still haven't graded your quiz from last week. But for last week's quiz, I'll add that as a bonus point to your midterm grade. So that should kind of help boost people. And so that will help. So will be added as bonus. So that will go in later to the grade book. Like I said, I'm behind on grading them, but once they do get graded, there'll be an adjusted score. And then I did want to offer some bonus points. And so this is probably looking towards the final. And y'all can kind of give me some feedback, because I had a couple of ideas. And so you can kind of tell me what speaks to you, or if we want kind of all three options. So something that I've done in the past is I've encouraged students to go to like the Oregon Caves or like Crater Lake and other like relevant scientific sites, and then just talk about it. Just either send me a picture or a paragraph. So we could do that. I was also thinking, I really want you guys to apply for like scholarships as well and internships. So I was thinking about offering a bonus point if you apply it to like a scholarship or an internship, and showed me that. So what do you guys feeling, or should we offer all of them as options? So people want all options, so let's do that. And so let's put 5 points per activity up to 10. So you can choose 2 of the activities and get 10 points, or do 1, or, and so let's do that. So we'll do a trip, do some cool site. I'll put scientifically relevant. And I'm pretty open to any possibility. There's like those fish hatcheries, Oregon caves, of course, or if you wanted to go to a museum, you know, Science Works or something, and just talk about what's there. So any sort of lakes, national park. And so for this, we'll do just like, you know, a little selfie, so I know that you were there, and then just like a short paragraph, you know, probably like 5 sentences over what you learned, what was cool. And so then we'll also do the other opportunity, and I'll separate them so you have kind of 3 opportunities to pick 2 choices. And so if you apply to a scholarship, oh, and I can't spell scholar. And so I would do something like not the foundation, though. So something like external. So look for that. Or if you apply for an internship, so does that give everybody kind of enough mix and match credits? Any questions on that, or other things that they feel maybe should qualify? All right, so that should help you for the final, since of course we won't have time for corrections on that, and hopefully keep grades boosted. All right, any other questions on stuff? So before we dive in, so we have a little bit left of chapter 5. So chapter 5 was like a really hefty chapter, because not only did they put stoichiometry in there, but then at like the tail end, they're like, oh yeah, don't forget redox reactions. So we'll cover that today and kind of hopefully get what we need to glean from there. But I did want to do some practice, because we didn't do a lot of like moles to molecules. And so let's try a question. So just a warm up here. So how many atoms of oxygen are there in 5.43 grams of carbon dioxide? So think about what information you might need to calculate for kind of your knowns. What are you trying to go for? What conversion factors do we have? So what information did you find was relevant for this question? What did you need to do? Georgia, did you start this? So where could we start the, Bianca, you want to?
The first thing I did was I converted the grams, the 5.43 grams into milliliters.
Excellent. And so, right, that's always a good place to start. So if we have grams, right, we probably want moles. Either we're going to be comparing mole-mole ratio, or, so right, we have atoms here. And so let me flip back to our flow chart, if I can find it. And so, right, if we're at our flow chart, and we're trying to, maybe look around what we should do. Well, we were given mass. We're trying to figure out how many particles we have. And then moles, right, is kind of in the middle of our way to get there. So yes, let's go with moles. So then how do we calculate moles?
I did 5.43 grams, and then I multiplied it by 1 mole over 44.01 grams.
And so that's just the molecular weight of CO2. So 32 plus 12. And so right on an exam, that's always a good way to get some points. If you're not quite sure what to do, calculate your molecular weights of everything involved. So that's always good information. Excellent. So now let's calculate this.
Is that 44.01?
Yeah. And your number could be slightly different or so. And so we punch that in and get 0.123. I'll round it to 1, 2, 3, 4 moles. Ah! No, go away. 1, 2, 3, 4 moles of CO2. And then now what do we do with this number? What relationship do we have? What did you say, moles to? Yeah, moles to particles. And so with that, right, we have our conversion factor, basically, so our relationship. And so anytime you want to go from moles to particles, you have 1 mole is 6.022 times 10 to the 23rd. And again, that's atoms or molecules or anything. You could say donuts if you wanted. And of course, right, we can flip it to go the other way, so let's do that. So if we're trying to go from moles to atoms, we need to multiply by the flip version of this so that moles cancels. And so now I'll do that. So mole goes on bottom, my 6.022 on top. And so now this is 7.43 times 10 to the 22nd. And so that's, right, molecules of CO2. But then, what did I ask for? So oxygen. So what can we do now to go from molecules of CO2 to atoms of oxygen? Yep. And so, right, we look at our formula, and if you wanted to do this explicitly, you could, of course, write for every one, molecule of CO2, looking at the formula, it contains 2 oxygens. So that's, again, how to formally write it. Or, of course, you can just recognize, let's just multiply it by 2, since there are 2 in there. And so that leaves us with 1.49 times 10 to the 23rd there. Do we want to do another kind of similar one? We'll go backwards this time once I... And let me write the answer. All right, let's try another one. So if I have 8.00 times 10 to the 24th, let's do molecules of ammonia. How much is this in grams? So asking for it in grams, I'll give you a few minutes again to try to work through that on your own. Oh, and by the way, I have homeless homework, chapters 3 and 4. I think it might be one on YouTube, but if not YouTube, you can put it back up. Oh, and I struck out my guessing. Where's yours? Okay, might have a winner. Where's everybody today? So let's start hearing, how did you guys approach this? So what should we do first? Yeah, molecules into moles. And right, you could go back to your little highway sheet, and we're going the exact opposite route as we did before. And so excellent, let's do that, molecules to moles. And of course, we're just using our same conversion factor. Moles goes on top, and that's 6.022 on bottom. So then did we get about 13 moles? I see some nods. So about 13.28 moles of ammonia. And then what do we do with this moles now? So grams, so how do we do that?
Multiply by the molecular weight.
So multiply by the molecular weight. And so what's the molecular weight here? Excellent, tag teaming on that one. And so let's see, did people get about 225? So I guess with sig figs we should round it 226 grams. Excellent. See everybody nodding on that one. So hopefully we feel a little better about that. So again, right, you have your mole highway to kind of help you. Moles is always a good place to be if you're lost. All right, so now let's look at the last end of chapter 5, which was, I mean, really redox reactions could take up a whole chapter. Well, let's try to get kind of a quick and dirty from this. And so this is really another type of reaction. And we'll kind of go back to our reaction types and see which ones are redox and which ones are not. And so redox reaction or oxidation reduction, so it's commonly abbreviated redox, so you'll see that everywhere basically, including scientific literature. And so that's just defined as a reaction where electrons are transferred from one reactant to another. And so many of these involve the reaction of a substance with oxygen. And so with this we can put, if we see a combustion reaction, that's probably a sign of a redox. But then there's also another really important one that's a redox. And so that's going to be single replacement. And then probably we just want to add to that decomp and synthesis, because usually, and I'll just put usually. And so the reason why we can see this, and we'll kind of go back to this, but usually all these reactions, like combustion or single replacement, they involve some sort of element that starts off in its elemental form and then becomes part of a compound, or vice versa. And again, we'll keep looking at this in more detail. And then let's add another little caveat on here. And so we'll say double displacement reactions are usually not redox. And so we'll go back and figure out why in a second. So let's try to figure out what the heck is still a redox reaction. What does this mean? And so it gives us some examples, but we still are not seeing any electronic bookkeeping right now. So we're just seeing something in its elemental form plus another substance in its elemental form. then they made a new substance. So we can at least figure out the oxidation state of our metal here. And so it becomes a 3 plus iron, and oxygen is -2. And so we can see this here for carbon and hydrogen. So organics get a little weird. We can calculate their oxidation state formally, and we'll look how to do that. But sometimes it's difficult to tell the true oxidation state without drawing the structure. And again, we'll look at what that means. And so we can at least calculate. So we'll go back to this one. We can see the CO2. So oxygen is always -2. That means our carbon is +4 formally. And so let's actually look at some rules for a second. So what are these oxidation state? And so kind of the first really key rule that we need to know before we analyze this is that our free elements have an oxidation state of 0. So anything in its elemental form, so right, sodium, could be chlorine gas, could be oxygen, any of our diatomics. So as long as it's in its elemental form, it's 0. So that's what they mean by free elements. So I'll just put that elemental form. And so now the rest of this oxidation state business we've kind of seen before. So this goes back to, right, our charges. And of course, right, we've kind of put our charges on our periodic table. Let's see if I have a periodic table on this slide. Oh, failure here. And so let me actually get a chart. That would be better. And again, you can read your oxidation states from your periodic table, so they follow along with the charges, and I'll just rewrite it to emphasize it. So hydrogen and our alkali metals are 1 plus, group 2 is 2 plus. We skip the transition metals, group 3 is generally 3 plus. Group 4, we have that 4 minus 4 plus switch here, and then it tends to go negative. But like your periodic table indicates, right, nitrogen has a few oxidation states, so that just depends formally how it is. So that's more like covalent compounds, same thing, right, phosphorus, sulfur. So all those kind of have positive numbers as well, depending on what compound they're in. And so again, rule 2, that's just equal to their charge. That's not too bad. Just like before, the sum of the oxidation states of all the atoms in a compound is 0, or whatever the overall charge is. And then so other rules, again, we'll kind of go back through all this. But we have our polyatomic ions. So of course, that has to equal the charge on the ion. And so that's how in this case with nitrate, so this is a good example. First, we always assign oxygen as -2, so that's another kind of rule. So these are kind of what they call priority rules. So fluorine is always -1, hydrogen is usually +1, and I'll put unless hydride. So there are metal hydrides. That would be -1. But then oxygen is always -2 unless it's a peroxide. So peroxides, oxygen would be -1. But otherwise, we base everything kind of off of the oxygen. So going back to this nitrate here, it has to equal -1. So we have -2 times 3 is -6, giving us a +5 for that nitrogen formally. All right, so let's go back to the start over here. And well, let's re-emphasize, well, why are double displacement reactions not redox? And so let's look at one example. And so a classic example is our silver nitrate plus sodium chloride to give us silver chloride plus sodium nitrate. And so now we can assign our oxidation states, just like we will be doing for redox reactions. And so this is always the first step. If you don't know whether it's a redox reaction or not, right, you have to assign your oxidation states and then compare. And so what's the whole charge on the nitrate? So this is a polyatomic. So what's this charge? Tell me off your sheet. What did you say? Sorry. -1. And so if this is -1, right, silver has to be +1. And then what's sodium's oxidation state?
+1.
So +1, and then chlorine is -1. All right, so this is what our reactants started off as. But then, right, they swap partners, and so nothing changed, right? So our silver's still 1+, chlorine's still -1, sodium's 1+, this whole nitrate is -1. So nothing changed. Everything is in the same oxidation state, which makes sense, right? Because all they did was swap partners, so there was no exchange of electrons. And so right now we can clearly see so everything, same oxidation state. And so then we can tell, right, no transfer of electrons. So the mechanism, right, for a double displacement reaction does not involve any transfer of electrons. It's just driven, again, by the formation of this precipitate here. Well, now let's look at an example that you've done that is a redox reaction. And you've done a few. So let's look at probably one of my classic favorites that we did. And so we had our single replacement zinc metal plus copper sulfate, which was that blue aqueous solution. And then you put them together, you saw the rusting formation of copper, and then the solution became colorless as zinc sulfate dominated. And so now we can repeat the exercise. So we'll go through the oxidation states. And so sometimes I like to just start with anything in its elemental form. So if I see zinc, okay, I know that's 0, right? It's a solid, so it's elemental. Same thing with copper, so we could just go ahead. Okay, that's 0. And then what's my copper in this substance here, copper sulfate? What oxidation state? So 2, excellent. And then, so that, if it's 2+ in this state, what's zinc when zinc sulfate in this compound? You said 2, right? Yeah. So 2 as well. And so, right, the sulfate doesn't change, so we can just kind of ignore that. And so right now we're seeing, okay, now we had an oxidation state change. So we had zinc started at 0, and then it went to 2+. And so now we can say, well, zinc lost 2 electrons, right? It became positive. And so you can imagine, right, we have to have proper bookkeeping. And so if we lost 2 electrons, something had to gain those 2 electrons. And so we see copper went from positive to more negative. And so copper gained those 2 electrons. And so now this is telling us, yes, right, we have a redox reaction, things are changing, oxidation states. But again, our big hint was that we started with something in its elemental form, and then it swapped to a compound, and we started with something not in its elemental form, and we got it back out in its elemental form. So that's always a good indication that's probably a redox reaction. And so single replacements are generally always redox reactions. So you can see that with like the chlorine gas ones too, or like the magnesium dissolving the magnesium ribbon being dissolved in gas. Let's just do that one. And so you can try this on your own. And so we did this in lab at some point, and we repeat it again. So you have magnesium plus our acid gives us magnesium chloride and hydrogen gas. So take a minute or two, see if you can assign the oxidation states. So who's losing electrons, who's gaining electrons, and we'll go over it. So what do we get for the oxidation state of magnesium on our reactant side? Yep, exactly. So it's in its elemental form, so 0. And then what about our hydrogen here? What's its oxidation state? So 1 plus, what about chloride? So -1. And then what about magnesium now in our product, or magnesium chloride? 2 plus. And so, right, chlorine still -1. So we can kind of ignore that one now. We know that's not changing. And then what about hydrogen on the end here? What did you say? 0. And so this looks good. So now we can tell, well, it looks like magnesium is losing electrons again. And so we should do some, let me balance this equation. So you have to balance the equation if you want your numbers to work out well. So now we can tell we're losing 2 electrons and then keeping it balanced. So hydrogen, each one is gaining 1 electron, but then there's 2, so there's your 2 electrons. So make sure that it's all balanced. So I'll put each hydrogen gains 1 electron, so times 2. And again, you just want to make sure you're gaining and losing the same number of electrons. So they have to be going somewhere. And so again, we can tell redox reaction. All right, excellent. Let's start looking at these other examples. And so now we can go back to this example. Well, we said that it was iron 3+ in our product here. And so now we can go back with our new information that we learned. Well, we said anything in its elemental form is 0. So 0, 0. And so you can see, right, iron is giving up electrons. And so that's generally what tends to happen is your metal gives up the electrons and then your other element picks them up. So, right, oxygen goes from 0 to -2, so becoming more negative, gaining those electrons. So now let's go back to the bookkeeping of these carbons and why I mentioned it might be funny. And so from our rules, hydrogen we said is usually 1+, and then we said it has to be neutral, except if we do, so 18, right, divided by 8. So this is how we can get some weird oxidation states for carbon. So we get the average carbon oxidation state in this structure is 2.25, and that's okay for our purposes. So this will happen probably only with carbon, where you get these weird oxidation states. And again, since we don't have a structure, right, we can't analyze it any further. We're just taking kind of the average value. So that's kind of weird for carbon, but that's okay. And so this is, again, why we have weird half fractions. So this is, again, more of a formality. And so now we can, let's see if we can look at it. Oh. And let's see. And so the organics can be a tricky one. All right, so this works out. So we have oxygen, so it goes from 0 to -2. So oxygen is gaining electrons, and so carbon goes from -2.25 to +4. So then it's giving up electrons. And so we could do our bookkeeping. And so, of course, this gets a little nasty. And so, right, each oxygen is gaining 2 electrons, but then there's 50. So it looks like we're looking at 100 electron transfer. And so we'll go each oxygen gains 2. And so again, right, bookkeeping gets kind of weird here. And so let's take the difference. So 4 minus a -2.25. So we get like 6.25 electrons roughly being transferred. And so times 16. And so at least that equals 100. And again, right, this number is weird because we're not looking at the structure itself. We're just getting the average value. But the important thing is that we're proving it's electronically balanced. And so now carbon, we'll say on average, goes from -2.25 to 4. So 6.25 electrons gained, or lost, I mean. So lost per carbon, again, roughly. So times 16 gives us 100 electrons transferred again. And so same thing, so again, right, this is another combination reaction or combination combustion, and so those will always be redox. So we have 0, 0, everything in its elemental form, and then 1+ for hydrogen, and 2- for oxygen. All right. And so then we want to just go through the vocab of this chapter. So any atom that loses an electron, we say that it's being oxidized. And then atoms that gain electrons are called reduced or reduction. And so this will be something that we'll do. So of course in this case, they laid it out for us, but we can do our little bookkeeping ourselves. So 0 for sodium, of course, in its elemental form, 0 for chlorine in its elemental form. Sodium goes to 1 plus, chlorine goes to -1. And so, right, sodium then lost electrons, so it became positive. And so then we can say it was oxidized or underwent oxidation. Meanwhile, chlorine, again, it gained those electrons, and we say it underwent reduction. And so there's a few handy mnemonics to help you remember. So you can pick which one you like best. So I'll give you 2 options. And so I'm originally from Texas, and of course we like oil out there, so we have this option. And so we can say oxidation is losing electrons, and reduction is gaining electrons. So you could use that, or maybe you don't like the fossil fuel industry, or maybe you just want some other options. So then we can use this Leo and then insert your favorite animals. So Leo the leopard or Leo the lion goes grr. And so then we can say losing electrons is oxidation, and gaining electrons is reduction. So either one you prefer, just as long as you kind of use that to help you identify who's being oxidized and who's being reduced there. Let people finish copying that. And so these notes are just emphasizing that again. So oxidation, we increase in oxidation state, so going more positive, and then reduction, you have a decrease, and let's just write that. So oxidation, go more positive, and then reduction, so more negative. See that with the sulfur. Blah, blah, blah. So then this is just going back how we calculate them. And so, right, this is kind of confusing because oxidation states in an ionic compound, right, they are the charges, so that's fine. And then all this is emphasizing is sometimes, right, you just have formal bookkeeping, such as with our covalent compounds especially. And so that's why, that's kind of where the distinction is, but again, it matches with what your chart says and everything. And so, right, it's trying to tell you that the distinction is ions are real charges versus, again, are kind of just bookkeeping methods, but they're very similar. All right, so then we went through the rules. Again, the big one was the elemental form one, and then the others we've kind of seen in practice. And so again, non-metals have oxidation states according to the table on the right, and the higher metals, non-metals take priority, AKA, right, assign fluorine's oxidation state first, and then base the rest off of that. And same thing, so right, you could, let's just do, so a quick example, if you had OF2, for instance, the first thing you'd want to do is assign this fluorine to be -1, and then, right, this would be an odd case where actually oxygen would be a 2+ formal oxidation state. And again, right, that's a covalent compound, so that kind of makes sense where you get these weird formal bookkeeping scenarios. And then, so we mentioned hydrogen. Again, that's usually 1+, unless you see those metal hydrides like aluminum hydride or anything like that, those metal hydrides. And again, oxygen is always -2, so always a good place to start. And if you see the peroxide, just know it's -1. And then, of course, right, our group 7s and 6 and 5 all follow like we expect. And so this we already saw, so this is just saying, right, they have to occur simultaneously, so that makes sense. If something is losing an electron, right, something else must take it. And so that's where we were calculating, right, are the same number of electrons being accepted as there are being lost. And then, so now we have these other terms, so now they're kind of the opposite. So if you have a reducing agent, it's going to be oxidized, which can be kind of confusing for people. So a reducing agent just means it's going to supply the electrons, and of course oxidation is losing electrons. And so I'm going to say, right, typically a metal, so potassium metal is used a lot as a reducing agent, sodium, and then other metals. So usually metals, I should throw in there lithium. So these are just standard reducing agents. And then, of course, they start off in their elemental form and then get oxidized. And then our oxidizing agent, so that means, right, it was reduced. So typically, your nonmetal, and so we kind of see that pattern down below. So we had looked at this before. So of course, they both started off in their elemental forms and then reacted how we expected. And so we said sodium was oxidized. So oxidation is losing electrons. So of course, if sodium was oxidized, then we can also say it was the reducing agent. Again, just meaning it was supplying the electrons for us. And then of course that makes chlorine the oxidizing agent, where it's going to be accepting those electrons. All right, so that was kind of a lot, but do we feel okay with this? Are there any questions that we didn't cover? All right, so that's kind of the basics of redox there. And so now let's kind of shift a little to chapter 6. And we'll see how far we get in chapter 6 this week. And so chapter 6 is all about energy and work and endothermic and exothermic reactions. And so now we can take it back to thermodynamics. And so energy is just anything that has the capacity to do work. So we can have potential energy, right? So we're drinking our soda there, and that has a bunch of sugar that supplies us, right, calories, and then it powers you to move later. It can, of course, also be, right, potential energy. So because of its position, my pen has potential energy, which, of course, I can let it go and it falls. And then we also know that energy can be exchanged between objects through contact. And so we'll talk about these collisions and, of course, how they affect reaction rates, which you're exploring this week in lab. And then work is defined as a force over a distance. So energy is equal to the work applied. So again, force times distance. And then other forms of energy would be heat. So heat is just a flow of energy caused by a difference in temperature. And you can also probably feel heat flowing in or out of certain reactions, which we'll go into detail. And so heat and work are two ways that an object can exchange energy with other objects. And so, right, we see that a lot where a lot of reactions either lose or gain energy as heat, but then sometimes, right, they may have to either do work on the environment formally or have work performed on them by the environment. So let's kind of define our types of energy. So kinetic energy is energy of motion. And so with that, we can also put like electrons flowing in a circuit. That's another form of kinetic energy. And so most people are familiar with kind of this energy due to motion. You can also look at this relationship, energy equals 1/2 mv squared. So kind of relating to kinetic energy in physics. And then work would be defined as our collision here, so that results in an energy transfer. And I don't know how many people play pool in here, but maybe you've seen that, right, with the billiard balls. So you chuck the white one at another one, and then sometimes the other one just goes on, right, while your white ball stays there. And so all that is energy transfer, and you can see that kinetic energy, right, go into the purple one here and hopefully land in the pocket. And so then thermal energy is then energy associated with temperature, so heat. And then, so like we mentioned, so potential energy is energy stored in an object. And so I mentioned food, of course, since who doesn't love food? But with that, right, we can really think more fundamentally of those bonds in a molecule, right? So we're thinking about making and breaking those bonds as we eat our food to get some energy back out. And of course, right, we mentioned gravitational potential energy as well. And of course, the other important concept is the energy can also be transferred. So of course, right, starts off as gravitational potential and then becomes kinetic. So same thing with our food, right? So it starts off as potential, becomes kinetic and heat. And let's see, so other forms of energy. So we mentioned the electrical, so we said that was also kinetic energy. People just tend to forget about this one. And then so we mentioned our thermal energy, so that's still kinetic. Light would also be considered kinetic energy, and so that could be associated. Well, you saw that, right, with the flame test. So you were burning stuff, and it was giving off light, and so that was associated with those transitions. So you excited the electrons by burning the crap out of them, and they released back down, giving you pretty light. And then, of course, nuclear energy. This is another form of potential energy, and except that would be exploiting, right, those nuclear interactions of the nucleus and all that force there. And then, of course, chemical potential energy, which is what we're really interested in this class, and just looking at the energy in our atoms and bonds. And so now we can kind of see where our units from energy come into. And so here's this 1/2 mv squared again. And again, our only relevance to it is the units. And so this is right from physics then, our physics convention. And so in physics, the mass is given in kilograms. And then v squared, so v is just velocity or speed. And so speed in physics is usually given in meters per second, except it's squared. And so now we can kind of plug into what the heck the units are. So we just plug in 1/2 kilograms meter over second squared. So that gives us kilograms meter squared over second squared. And so that's what a joule is. So this is pretty useful. I don't know if some of you will go on to take physics later, but this is always a good place to come back to. So this is where the joule comes from. So now that's why a joule is also equivalent to kilogram meter squared over second squared. And so you might see that conversion, especially in physics, going back and forth from kind of this kinetic energy formula to joules. And so that explains the units on stuff. And so a joule is just the amount of energy needed to move a 1 kilogram mass then at a speed of 1 meters per second. And so this is also equal to our Newton meters, but I won't talk too much about Newton meters. They don't really come up too much in chemistry, but if you took physics, you'd probably do more Newton meters. And again, it's all just related to joules. And so now more, this is either depressing information, at least I always get depressed when I hear this. So a calorie, so this is not your food calories, so this is another calorie, so this is little calorie, is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And then so 1 kcal is the energy needed to raise 1,000 grams of water 1 degree Celsius. And then the depressing fact is your little food calorie on the back of your package is equal to 1,000 calories, right, or a kcal. Yeah, so then I get depressed, right, thinking about all that energy that I just ate with all my calories. So that's probably why, right, you got to go work out and burn off a ton of, or work out a lot to burn off a small amount of calories. So 1 kcal is equal to 1 food calorie, and so you can think about that. And of course, when you're thinking about this 1 gram of water, you can think about how they quantify calories, right? So you can like burn a potato chip, for instance, so that'll burn, right, a good while since it's nice and fatty. And then if we had a nice calorimeter experiment, we could, of course, quantify how much that water was raised in temperature based off of our little chip. And then that gives us a calorie. So these are good conversions. So this one you'll probably run into, and along with this one and this one. And the kilowatt hour, it's here as reference, but in case you find a word problem involving kilowatt hour, but we generally don't use it too much in chemistry. And then, so then this brings us to our first law of thermodynamics. And so that's the conservation of energy. And so the first law is that energy is conserved. And so that means the total amount of energy in the universe is constant. And so that means, right, that we can't design a system that will continue to produce energy without some sort of input. And so you guys are familiar with that, right? Like a perpetual motion machine. Have you heard of that and why? So I'll just put the Wikipedia page on there, but yeah, again, it's just a hypothetical machine that could just do work infinitely without an external source, but of course, right, it violates thermodynamics, but it's kind of interesting to think about. There's the theory. And so now let's look at, well, what are we really interested in? And so that's our bond energies. And so, of course, we've kind of mentioned chemical reactions involve breaking reactant bonds, and then we make some new bonds to create the product. And so we can figure out basically how much does this reaction cost. And so this is our delta heat of our reaction. So this is basically, is our reaction endothermic or exothermic? That's our basic question here. So will the reaction get cold if it's endothermic? So endothermic meaning it requires some heat input to go. Or is it thermodynamically favorable? Is it exothermic, meaning it will give off heat? And so we can estimate that by comparing the cost of our old bonds to the income we get from making new bonds. And so the amount of energy it takes to break 1 mole of a bond in a compound is called the bond energy. And so the calculations that we'll be using are from the gas state, and then assuming a homolytic bond cleavage where each atom gets half of your bonding electrons, so that would look like this. So my half arrow to indicate 1 electron movement, and again a homolytic bond cleavage. And while we're talking about homolytic, let's just define heterolytic. So heterolytic would just be something that does not break like this. And so one good example would be this BF3 ammonia compound. And so I drew it like that to show, right, that nitrogen is actually donating both of its electrons in that bond. So we could go back to our Lewis dot structure real quick. And so, those 2 electrons, that's what's going to be donating to BF3, right? If you look at BF3, so that's its Lewis dot structure. So it doesn't have any electrons to participate in bonding. So hence why this one would result in heterolytic cleavage. But again, these are kind of rare scenarios, but I just wanted to point out what would be heterolytic. So most of the time, right, it's always going to be a homolytic cleavage. And so then we'll do our bookkeeping. And so what happens is we have our energy from our bonds broken. And so breaking bonds requires energy, and it tells us that there. So, right, we have to put in energy to break that bond. But then once we form a bond, so that's considered thermodynamically favorable, and so that gets you a negative value, so energy is being released, favorable. And then we'll add these values all up, so we'll kind of work through what that looks like, and then that tells you the overall delta H of the reaction. And then we'll get to say exothermic. So if the overall reaction is exothermic, we'll have a negative value, and if the overall reaction is endothermic, we'll have positive. But we'll kind of see that. And so before we look at the numbers, let's just at least discuss some general trends. And pretty self-explanatory, I think, for the most part. So of course, in general, the more electrons 2 atoms share, of course, the stronger bond. And so triple bonds are stronger than single bonds. So you can just see that trend. Same things, right? Carbon, nitrogen. So obviously the triple bond has the highest energy. And so same thing, the shorter the bond, the stronger. And so we see this with bromine, fluorine, bromine, chlorine, and bromine, bromine. And so these are shorter, especially from fluorine having that small radius. So that has 237 for the bond strength versus your larger bromine, bromine. That's 193. And so as you might imagine, so they get weaker down the column, right, as that radius gets bigger. But then they get stronger across the periodic table. So that kind of follows with our electronegativity trend. So as we fill up that shell, that's going to give you a stronger bond. So as we fill up shell, right, i.e. if we fill up the 2p, so aka that's why fluorine, right, is very electronegative, so that's going to give us a strong bond as we fill up that shell across the period. And so, right, for these calculations, I would have to either give you a table or, of course, right, I let you use open notes. Although probably on an exam, I'll just give you the relevant bond energies that you'll need. And then I do want to point out, so the only exception is this little 799 in CO2. So CO2, so carbon dioxide, has pretty strong CO double bonds. And so that's why they have you use this different value for CO2 versus just another CO bond, like a carbonyl or something. All right, so let's go through this. And so this is kind of giving you your energy diagram. So this is your overall reaction energy. Let's do this example before we do the practice. And so you just want to maybe draw what you're doing out. And so, right, we're starting with methane plus chlorine gas. And so I'm just going to draw this explicitly for now so we can kind of see what bonds do we need to make and break. And we'll do our bookkeeping. So we start with methane, and then it looks like we're just going to break one of those CH bonds, right, and then replace it and make a carbon-chlorine bond. And then we have to make an HCl bond. And so maybe you want to highlight the differences. So now I can clearly see, okay, we're going to have to break this, and then we're going to have to break this, and then we're going to make a carbon-chlorine bond, and then we're going to make an HCl bond. And so now let's do the bookkeeping. And so I like to keep them kind of separate before we add them. So let's put, right, our bonds broken here. And so now we can do our bookkeeping. So we have one CH bond. And then just go back to your table. So it's a single bond. And so it looks like that's 414. And so this is in kilojoules per mole, by the way. So at least be aware of your units. Then we have to break a chlorine-chlorine bond, so that's a single bond here. If I can find it, so no, that's carbon-chlorine, chlorine-chlorine, 243. So one chlorine-chlorine. All right, so it looks like, I'll go ahead and tally up how much energy we had to put in. So 414 plus 243. So that's 657 to break our bonds. Oops. 657 kilojoules. And so let's see how much energy we got back out, though, from our bond formation. And so now we have carbon chlorine. And so it looks like that's 339. And then one hydrogen chlorine bond. Let's see, where's that? So 431. And so I'll add those up. 339 plus 431. And remember, this is all negative though, since we're getting energy back out. So this is going to be a negative 770 kilojoules. And so now, right, our overall reaction, now we just have to add up, right, bonds broken plus bonds formed. So we have negative 770. So I'm just trying to make it negative plus our 657. And so I get an overall delta H of our reaction of negative 113 kilojoules. And so again, it's negative, so this is telling us it's going to be an exothermic reaction, aka it will feel hot to us as it's releasing that energy as heat. And so this is good because we kind of expected that as well just from this little schematic. So it's showing, right, that your products are lower than your reactants here, and that's what we calculated. All right, so see if you can try that then for this process. So I'll give you a minute to copy this reaction, and then I'll scroll back up to the bond energies. Just make sure you write it down. So it's methane gas plus 2 equivalents of water to give us 4 equivalents of hydrogen and 1 equivalent of CO2. And so now I'll scroll up, trying to show you everything. Not sure I can make it any bigger. If you need me to read a value too, I can just do that. at least kind of start going over this. And so what you might want to do, especially, if you're new to these calculations, is just write, visually what's going on. So I would write our big methane. Again, just kind of simple enough so we can see the bonds. And then we have 2 waters. And so, right, we could even draw out 2 waters physically again so we can see really clearly what we're doing. And then we want to make 4 hydrogens, so I'll write them out again really explicitly. You don't have to do this, but I kind of like a good visual while we're just starting. And then we have our CO2. And so now we can just do our process again, and you all can help me out. And so now what bonds do we need to break? So looking at this methane, how many CH bonds do we have to break? You said 4, right? Maybe it was just the hallway said 4. So we have to break 4 bonds, right? Because we can compare. So we had a carbon over here. We only have 1 carbon over there, but there's no more CH bonds. Okay, so there's our first start. And so let's do that. So 4 CH bonds. And now go back to our table. So it's 414. I'll scroll back up all the way just in case. 414. Just wanted to make sure. And then, of course, times 4. I'm just going to do the multiplication now. So 1656. And so now looking at my waters, so same thing, right? We have to break, so 1, 2, 3, 4 oxygen-hydrogen bonds. And so let's see what an OH bond is worth. So 640, or 464, sorry. 464 kilojoules. So times 4 again should give us a large number. So I got 1856 there, so now I'll add these two. And so I get that we have to put a total of 3,512 kilojoules in. So 3,512 kilojoules. So now let's compare our bonds broken. Definitely need more like fun colors. So now bonds formed. And so we can do the same process. And so, right, we basically broke everything. So it looks like we'll have to reform everything as well. So that's going to be 4 HH bonds. So let's see, each hydrogen bond is 436. So times 4. So about 1744. And then we'll form 2 CO bonds. And so this is where we want to use that special value. So they gave us that 799 for CO2, so that's what we'll use. So 2 CO of 799. And And so that gives us 1598. And so now I'll add to get our total. So 1598 plus 1744. So 3342 for my total. Let me just write some numbers. And again, that's a negative sign, right? Because that was energy we got back as formed. And so then we want to add our two numbers together to get our overall delta H of our reaction. So again, that's positive 3,512 plus my negative 3,342. And so then we need 170 kilojoules to make this reaction go. So it's endothermic. And so we'll put endothermic. And if it's endothermic, right, it would feel cold to us since our body heat would then be helping to supply, right, that 170 kilojoules per mole to make that reaction go. Any questions on this process here? So hopefully not too bad, you know, just again, write everything nice and explicitly so you can kind of see. Otherwise, it's just a lot of adding. And then, so with that, we have all these little energy diagrams to help us kind of show, again, this exothermic versus endothermic process. And so in this energy diagram, now it's just showing us another way of energy flow. And so if we have an exothermic process, so our reactants then are higher in energy. So this is just overall internal energy. And then, again, in this case, we're going carbon plus oxygen gives us CO2. And so the reactants have this energy, and then CO2 is less. So again, that change in reaction gives us energy out, so negative, and again, exothermic process. And then the other thing that this is showing us is, of course, right, the energy then has to flow to the system. And so, right, if energy is leaving the system, so it's negative, then that energy goes into the surroundings. And so that's where you, again, right, feel that hot reaction. So then the system is losing energy, but then the surroundings then gain that same amount of energy back. And again, we'll put, right, so then it will feel hot to you, and, right, could even heat up your body temperature or whatever else if you were doing this with, like, a calorimeter. So then you get that same energy increase. And so this is another reaction diagram. So this shows us our progress of our reaction over time. And so let's look at this because you may have to draw one on your exam. And so we start off with our reactants, so they're just put at their energy. And so then we have this little hump here. And so this is equal to our activation energy. And so that just goes from your reactants to this transition state. And so, right, this activation energy is just defined as how much energy you need to kind of get that reaction started and get to this transition state. And so this transition state is just a temporary, fleeting position, and so it kind of depends on the compound and on the reaction, whether you can, like, observe this transition state or not, or how fleeting it is. And so basically, this is just our kind of transition point. So sometimes you can, like one example is if you're doing that methane reaction plus chlorine gas, then you would have some sort of transition state where you're losing that one hydrogen and replacing it with a chlorine. And so again, right, this transition state, so this would just be fleeting, and so just kind of drawing this compound that obviously doesn't exist because we have carbon with 5 bonds to it, but it's just that transition period of hydrogen leaving and chlorine coming on. So that's one example. So once we get past the transition state, then we go to our products. And so we're still looking at an exothermic reaction. So maybe we should label this exothermic up top. And so if it's exothermic, again, it's releasing energy. So the products are lower than the reactants. So there's your delta H. You could subtract, right, products minus reactants. That gives us a negative value for delta H, aka an exothermic reaction. And so, right, you might want to write that down. So exothermic products, lower in energy. And so now let's look at the diagrams for an endothermic process. And now, right, it's gaining energy. And so looking at the reverse, so going from CO2 and then doing a decomposition to make carbon and oxygen. And so now that would be an endothermic process. Notice how your reactants are on the bottom now. And so products, again, higher in energy for an endothermic. And so same thing, right? If your system now is gaining energy, well, that energy has to come from somewhere. And so that's going to be from the surroundings. So then, right, it's going to be flowing from the surroundings to the system. So now delta E of our surroundings is negative. And so that's, again, right, why it feels cold. And so I think it's ammonium chloride. If you dissolve it in water, it gets cold, if I remember correctly. And so, right, that's what makes it feel cold. It's an endothermic process, and your body heat is losing energy to power that endothermic reaction. And so now the energy diagram is pretty similar to our exothermic. So again, transition state. Notice it's the energy from the reactants to the transition state up here again. And except in our endothermic reactions, now our products are higher in energy. And so maybe you want to write that down. So endothermic, right, higher in energy. And then, right, your delta H of your reaction then is products minus reactants again. So in this case, products are higher, so then you get a positive value of delta H, again, corresponding to endothermic. Okay, questions about these diagrams? And so now we'll talk about kinetics. And so kinetics is somewhat related to endothermic, exothermic, but not quite. But basically, our kinetics is how fast our reaction is. And so for chemical kinetics, we always have to measure the reaction, but we can, of course, observe some trends. And so the rate of reaction, of course, is how fast the reaction makes products or uses reactants. And so this is important, especially in industry, if you're trying to make something. And so being able to control the speed of the reaction is important, right? You don't want it to go too fast either, then it might be a runaway reaction. Obviously too slow, we'll never make anything, and that's inefficient use of time. And so you explored, or will explore, some of this in lab. And so one of the factors affecting reaction rate is concentration. And so this generally makes sense. So the greater the concentration, right, the more collisions then. So of course, if you have more atoms floating around, that just means, right, they have to kind of travel less to meet another molecule. And so you also have to think about, right, what has to actually happen when a reaction occurs. So not only do they have to meet, right, but they have to meet at the correct orientation with the correct energy. So we mentioned that transition state energy. So all that has to be correct for the reaction to occur. But of course, with our greater concentration, we have a greater probability of that happening. So of course, greater concentration equals greater frequency of collisions. And so we look at concentration in lab with our little molarity. So we still haven't quite defined molarity, but you've seen it a lot in lab. So you'll compare, right, 1 molar versus 2 molar versus 3 molar. So of course, right, higher numbers, more concentrated. So you kind of see what happens. You can do the same thing with gases. So gases depends on the partial pressure, but again, all we need to take away right now is higher pressure, higher concentration, and of course, right, more collisions and more reactions then. And then again, concentrations depend on the molarity, which we will come back to solutions, if not next week, then the week after, but very soon. And so other factors that affect the reaction rate. So of course, temperature, and this is kind of just a fun fact. So they just say, in general, for every 10 degrees Celsius rise in temperature, the reaction speed doubles. But again, all we care about with temperature, so increased temperature. So if we increase the temperature, that leads to faster collisions. And so with faster collisions, that's going to be more collisions. And right, temperature is also related to kinetic energy. So not only do you have more collisions, but you also have what I would call more productive collisions, right? So we mentioned again, that has to meet that transition energy threshold. So if you're at a higher temperature, it's going to be at that threshold more likely. So more productive collisions. Let's see. I guess we can talk about catalysts. We still have 10 minutes left. So catalysts, these are just substances that affect the rate of the reaction without being consumed. Can anyone in lab today name a catalyst that you used? Yeah, the potato. So the potato is a good one. So we had our hydrogen peroxide, right? And then we added a potato. And so that catalyzes our decomposition. And so that made oxygen and water. And so you could see that bubbling in lab. And if you haven't been in lab, we did that previously another week. But we can see, right, the potato is not involved. It just provides a mechanism. And so what's interesting, too, is they actually create a whole different pathway. So, right, it says here they create an alternative mechanism. And so really, right, it's like creating a whole new reaction pathway. And so one example would be this ozone plus oxygen radical to make O2. So this is normally very slow, but then it can be catalyzed with chlorine. And so catalysts are usually consumed in an early mechanism step, and then they are recovered in a later step. And so this is a really good diagram because, again, this is telling you what's happening. So again, uncatalyzed, usually you have this sort of transition state, and usually why you want to use a catalyst is maybe this activation energy is just too high, right? So then your reaction pathway is not favorable. But now the catalyzed pathway, usually it kind of breaks it down into different steps as kind of shown here. So maybe 2 steps that are a lot lower in energy, so then it can actually happen. And so most catalysts are used to speed up a reaction, and so usually we just say the term catalyst. They called it here a positive catalyst. But you can also have a catalyst that slows a reaction. And does anybody know the other name for that other than negative catalyst? Another word. So it's called an inhibitor. And so again, generally we're trying to speed up a reaction, but just in case we have that term there. And so a homogeneous catalyst would be all species present in the same phase. And so an example of that would be, right, this reaction that's shown here. So everything is in the gas phase, all reacting. And then a heterogeneous catalyst, so species are in different phases. So one example would be like our potato, right? Because you have your potato that's solid, but then your hydrogen peroxide is a liquid. And so, right, other heterogeneous catalysts would be like your catalytic converter in your car. So your catalytic converter, right, is a solid piece of metal, and then the gas is passed over it. And there's a lot of different, arguments for different types of catalysts. So homogeneous catalysts, that's a lot of what research goes into, but of course, there's always the recovery problem. So how do you get back out the catalyst? And, again, it depends on your reaction, so how tricky or hard that is. Sometimes they just trash the catalyst because it's too difficult to recover. And again, a catalyst might have anywhere from like a 1% to 10% loading. So that would kind of be, right, your mole ratio where you use either, again, 1 to 10%. And heterogeneous, so this is kind of what industry tries to go for in an ideal world, since they're different phases, so that's generally easier to kind of separate and keep, reusing that catalyst. All right, in our last few minutes, I at least wanted to show kind of other catalysts and how they make new pathways and give you some idea. So these are really important catalysts that are used in olefin metathesis, so making these different double bond reactions. And so these people got the Nobel Prize for making these catalysts. And so you can kind of get a sense of how they make a new pathway. So you can see, right, you have 2 things reacting, make a new thing. But this catalyst provides a new pathway by providing some place for these reactants to attach to this metal here. So you have some molybdenum with our carbene or other base, and right, they attach here and then do their reaction and then kind of release. And so again, we won't go too much into it, but that's gives you a taste of how they're powerful and how they work and how they completely change the mechanism of the reaction. All right, we'll stop here, and then Wednesday we'll finish up with our reaction rates and hemoglobin and Le Chatelier's principle.